So if this helps you, awesome. If it doesn't, it's just good to know anyway, because this is how you solve a lot of recycle loops or a lot of convergence problems kind of in general with process simulators, and how to alleviate circular references in Excel, because that's actually what happens in process simulators. They just don't use that terminology. So I found this online, and so I'm just using it to describe how to go through recycle loops, because if it's from a Pro 2 professional or employee, it's better than anything that I can make up. So I'm going to step through their presentation, and I'm going to post this on Canvas. I forgot to before. So yeah, in this, they just talk about quickly recycle background, how a simulation would solve it, the recycle convergence, and different strategies for convergence, or to achieve convergence. So from a process simulation point of view, recycle stream is a term denoting a process stream that returns material or enthalpy from a downstream process unit back to an upstream process. So this is a thermal recycle for your reboiler. It comes back and it heats the feed. Now that one is actually pretty easy to solve. That's just reusing energy, and it's actually a different line. You might have to supplement that, or it might be just a difference in Q, and you can fix that fairly easily. The real pain with recycle loops is composition. Because mass has to be conserved. You have mass feed inlet and your product outlet. Everything else, so this mass has to equal this mass, and that's why it's really tough to converge recycle loops. So looking at this, you have recycle 1, recycle 2. These are just different units, and of course streams. So you can recycle between U3 and U2, U6, U5. If you have an interconnected loop, then this downstream U6 feeds to U3, and that affects this recycle loop here between U2 and U4. If it's a nested loop, of course, then it's inside. So there are three main categories for recycle loops. Now the tear stream. Remember first Friday when I talked about that? Yeah. Sure. Some not, some do. It's cool. It's back in the slides. It's back on the video. So a tear stream, any stream that opens a loop, you virtually cut that, and you have now technically an outlet stream, R1 out, and an inlet stream, R1 in. It's that stream that Pro 2 or any process simulator will update until 2 consecutive iterations are within some tolerance. Now that doesn't mean you can expand your tolerance to make it solve, because then you're still 100 pounds an hour or whatever off. Your mass balance still won't work. A tear stream technically is not a recycle stream, because those are 2 streams. So with this, and there's nothing wrong with using a tear stream to solve recycle. You just have to know what you're doing so that you solve your mass balance. Chances are you solve your mass balance, your energy kind of follows with it. So the tear streams for this process. You can break R1 and R2. So if your tear streams are R1 and R2, the calculation sequence in its standard process simulator, it'll solve U1, and then it looks at U2 through U6 kind of all at once to make sure that this stream 2 equals the mass of stream 7 before it solves unit 7. Does that make sense? So it has to treat U2 through U6 as a one big loop.
You're still doing overall from U2 to U6?
Yeah. So these parentheses signify that it'll step through once, and if S2 does not equal S7, it steps back and it does it again, changing the values of the recycle, the fractions leaving U4 and U6. So it needs to get those ratios correct to achieve the proper mass balance between stream 2 and stream 7. or we can tear stream 4. If that is the case, then it solves unit 1 first, 4 and 5, because this feeds back to U2, and U6 also feeds back. So this is a little more of a complicated example. It can get really complicated really fast, is what I'm trying to highlight. So now we're going to draw something on the board really quick. So I have an inlet to a mixer. I have a heat exchanger, a divider, and a product stream. I have feed F, product P, and from this divider, I'm actually going to feed back part of that flow. So this is my recycle. Now, if we want to put numbers to this, we say, all right, we have 1,000 kilograms an hour of feed. And if we get to the divider block, we have a couple options. We can specify how much product we want or how much we need, or we can specify recycle. So if this goes through, initially this recycle stream is 0. So you have to initialize all recycle streams. You have to give it an initial value that's not 0 so that it can actually add the two numbers appropriately. Otherwise, you just feed 1,000 kilograms an hour straight through and you bypass this entire thing. So if you specify your product at anything, say 500 kilograms an hour, is that going to solve? No. Right. So you are going to need purge streams, potentially, or you're going to need to split the recycle as a tear stream. So if you do that, choose a different color. So now we have RA and RB. Out of this divider, we can specify how much we want to recirculate or recycle. This will end here. You can then look at the inlet of this stream and see if it matches. And it'll continue to solve after you get rid of this particular specification on the product stream. It will solve this so that you have an achievable mass balance. You can do it another way. If you specify that 500 kilograms on the back end, you're going to have to change something. Just like Dr. O'Connell was saying. A series of equations, series of unknowns. This is overdefined as it's written on the board right now. So what can we get rid of if we have to achieve a certain product flow? What can we get rid of to make it solve? The feed. Yep. So if we get rid of the feed, now this looks a lot more manageable because we can just set the feed rate to whatever it needs to be so that we get 500 kilograms an hour out. Now, a lot of this is very easy to say. You're like, okay, well, how do I actually do that in a program? I'm going to post a ChemCAD video on Canvas that goes through recycle loops and exactly how to solve this using this tear stream, or cut stream is another term for it, application. But we step through this just a little bit more before we get into that video. Okay, so a sequential modular approach. that's where it solves one stream or one unit after another to make sure the mass balances out. Again, that's simultaneously modular. It looks at the flow sheet as an entire kind of block and optimizes based on that. Simultaneous modular approaches require more computing power, but with a lot of computers now, it's a little easier to do. So you can step through individually and say, and change your recycle loop. So you can step through and say, okay, what if we have a recycle loop here or there or anywhere on a flow sheet? That takes a long time. That's this sequential modular approach. That's backwards, not forwards. The sequential modular approach. So this is an enormous spreadsheet that tries to have all of those recycle loops available. That's a huge pain, and it takes weeks. I'm not even saying days. It takes weeks or months to try to solve something like this. So these sequential solvers, a bunch of other stuff. Right. So minimum tear stream algorithm, that is what Pro2 uses specifically. It's very similar to what ChemCAD uses, very similar to what Aspen uses, and as well as SuperPro. I'll save time and not read off of these slides. I will show you the video in ChemCAD really quick. It's about a 5-minute clip, and then post it. But I want to leave time at the end to talk about how to download ChemCAD and use it on your own machines. The problem is it only works on real computers, not Macs. Kidding. Shots fired. Get rid of that camera now. Not yet. I deactivated all of that stuff.
Minus 500 kilograms produce. Take the different cut stream.
So on this file or on this video, between about, I don't know, 5 and 15 minutes into the video, he talks about basically what I did and how to create tear streams, how to create cut streams. So in ChemCAD, it will turn a different color. So this, you can see, is red. So this mixer here and this divider here, it doesn't converge. That's why it's a different color. Now if I fast forward a little bit, down here you can see that he's duplicated it, but now he has those additional, that cut stream. He's created this RA and RB. Now when you do that, you can kind of choose in a divider block or mixer block where it takes that flow rate or how it directs that flow rate from a divider. So it's not worth the time right now to watch this video, but please look at this video if you have any questions about recycle loops, because while this is ChemCAD specific, it kind of goes for all process simulators. There it is. So from this, you can see this is the problem. When you exit the divider here, Euler's method, a little bit of calculus. Sound familiar? Okay, cool. Ish. All right. Ish is good enough. This xi plus 1, that is your second iteration because xi is your initial or your initialization of that recycle stream going back and feeding into the heat exchanger. So that's why you have to give it an initial value so that it can properly update every time. Typical process simulators have about 40 to 50 iterations before it says, no, I'm done, I can't do this, it's not going to converge. You can change that, but 40 to 50 is default. So if you have any problems with solving your recycle loops, let me know after you've taken a look at this as well as this that's online. So this again is Pro 2 specific. Let's see. Yeah, it goes through a bunch of the math, and the math doesn't really help you when you're looking at the flow sheet itself. And since we now have access to ChemCAD, this is actually one of the best videos for recycle convergence. I still want to talk to teams, so I'm actually going to stop there. But before I do, are there any kind of general questions on recycle loops? I know that it's not incredibly helpful, just this little 20-minute discussion, but there's too much out there to squeeze into even a 3-hour lecture about how to solve recycle loops. Again, this is one of the best videos that I've seen to solve and to target your convergence. And the fact that I found this is good. Oh, but
Can you explain again why do you split the recycle stream into RA and RB?
yeah. So if you were to continue with recycle stream R, the way it's in blue up here, then you don't have an initial value to give the mixer. Because this is not an open stream like your feed. So you can't tell this, I want this to be 100. Or I can't tell this to be any specific value. This is a function of the divider. If it's a function of the divider, then that means in this block, or whatever separation unit op this is, you can specify the ratio or the absolute value of those streams. And when you do that, then it feeds back. And if you don't have a purge stream or a drain or some extra stream, like that, then your mass balance will not solve. Because the extra mass that you have fed doesn't have anywhere to go, so basically it accumulates. So by cutting this stream into two separate ones, say RA and RB, you allow this to temporarily be just an exit stream, some sort of byproduct. That you can then update this stream.
You can assign it to any value for RB or?
Yeah, so you can look at the output of RA and then update RB. It's an iterative process, and this is by hand if you do it the tear stream way. And this is the same way you would do it in Excel. You'd have a cell that you focus on, so you change everything upstream, and based on that value, you update your new system or your new iteration. And you can tell by updating that value whether it's going to converge or diverge. Kind of just by looking at the values. Did that answer your question? Hello?
And for the cell that you create, you would have to leave it off to the side. You wouldn't be able to, once you figure out the values that they're equal, you wouldn't be able to make them reference each other again, because then that'll just create the circular dependence, and then that's an error, right? It'll create circular dependence within that loop.
Right, so that's what this does. This is the exact same method in Excel as creating a circular reference, because it loops around and it's calling on itself to give it a value. But if it can't give itself a value, then it fails and it diverges, or it does not converge.
Of course.
And every recycle stream is a little different. Sometimes you can specify your product flow. Sometimes you can specify your split. So like in a separator, membrane separator, something like that. Based on what you have available as a real unit, you can specify, all right, our retentate is this, our permeate is this. So that can solve a straight recycle loop, and you don't have to use the cut method. There are others that are very hard to do. But if you have a gas, you need a purge stream if you want it to converge. If you have a recycle, especially with a compressor. That extra energy and entropy generation is going to make everything fall apart. So you need a purge stream with gas streams. There was another question back there. Yeah.
Does the video tell us when to add recycle versus or how do we determine when to add and when not to add?
That is going to be mostly based on economics. So I know you asked me that yesterday, and I thought more about it. You add a recycle stream to increase efficiency. You can add a stream to increase your profitability analysis. So rather increase your ROI, your payback period, whatever your economic metric is, to optimize that or increase it.
So would it safe to say that, let's say you don't add a recycle stream and your efficiency is below what your desired is, then you want to start to think about adding in recycle streams?
Yeah.
To get to like purity or...
Yeah, so 99% for your process is what you would need. So if you're hitting 95, if you add a recycle, that could really help out. Also, you have environmental audits and environmental analysis that will kind of dictate, okay, we just can't dump hydrochloric acid out as a drain. It can't just be that stream. That has to be recycled and go through some sort of post-treatment process. If you have anything that is caustic, hazardous, basically, if you don't want to breathe it in or you don't want it to touch your skin, you should not be dumping it out from your process. General rule of thumb, that's just my own opinion, but there are set guidelines for that kind of stuff.
What if we get to a point in our project where we realize that we have to add a unit operation, and we're done with the MEB at that point? What happens?
Redo it.
You got to add it in.
I mean, that's what it is. I'm just curious.
So that's where the whole kind of strategy of focusing on the reactors comes in, because if you have to add a reactor, then you messed up the beginning of the first part. Unless you add in contingency or duplicate or something like that. Because again, the way that you would solve something like this is it'll tell you your available volume or your required volume for a reactor. That volume is just the total space you need. You can, in your PFD, have 3 reactors be present that represent reality, but you can only need 1 reactor, maybe in SimSci or whatever process you have. So it's a lot easier to add fluid movers, pumps, and things like that. So really focus on reactors and separators, and then start adding pumps, fluid movers, because the way that all of these solve is it will assume that you have a pressure gradient whatever. Something's moving the process downstream. But if you just have reactors and separators, that is a horrible flow sheet, and that's a horrible design, because you have nothing to move the fluid through the process. You have no pumps, compressors, anything like that. So you need those. You just need those, period. Any question? And I'm going to address this, the recycle stuff, better in the context of ammonia synthesis when I show it in class the next 2 weeks. I think Mr. Sinha is going to go over drafting and proper drawing technique this Monday, and I'm going to finish off lecture with proper presentation techniques. But I'll put all of this in context as well as the past 2 weeks of Monday lecture. So any more questions on recycle loops or anything right now?